He's going to be talking about an experimental framework for Pragma Handling in Clang.
Yep. So thank you for the introduction. As you said, I'm from the University of Innsbruck, and so first of all, I have to give you some background information of the project I'm working on. Basically, this work was done as a part of a bigger compiler project that we are developing in Innsbruck, and this is called the EuroLLVM compiler. You could find the link over there. And basically, this is a source-to-source infrastructure, and we use Clang as a front-end for loading C, C++ codes, but then we just transform the Clang AST into our own intermediate representation, which is much higher level with fewer nodes than the Clang AST, and we call it Inspire, which stands for Insieme Parallel Intermediate Representation. And this parallel there means that our main targets are HPC languages, and our research focus on OpenMP, MPI, and OpenCL mainly. So we use our compiler to provide transformations which apply to input programs which are already parallel. And as I said, this is currently developed by University of Innsbruck, and you could find information on this website. So now to the main topic. So we've seen a lot of, during these 2 days, a lot of talks were involving Pragma Handling, and so I start by describing what pragmas are. I think most of you are aware of why and where we use pragmas. And I found this definition from the GCC webpage. And ideally, we can think of pragma as a mechanism to extend either the knowledge of the compiler on a specific statement or block of code that the user can provide to the compiler, or it can be used for instrumentation issues and so on. And I distinguish between two kinds of pragmas, between the whole range of pragmas you can think of. And the first category, I call it positional pragmas, not positional, associative pragmas, let's say. Basically, this is the example 1, where we have a pragma which refers to the following statement or declaration. If you, for example, have a pragma which applies to a function definition or a static variable declaration outside the scope. And in this case, the semantics of the position is important. For example, in this case, this parallel for, it must be followed by a for statement, otherwise this pragma is semantically wrong. So the compiler should fail, or at least give a warning that he was not able to apply the semantics of that pragma because he was expecting a for statement afterwards. And there are other kind of pragmas which, for example, this OpenMP barrier, where the important aspect is not what it's following or what it's before that, but the exact position within the code. And here, for example, we are enforcing the compiler to add a synchronization primitive at that specific position. So the compiler should not move it around, and it should comply with that position. So what are the motivation of having pragmas? So basically, as a researcher, we love to add new pragmas because we know that we think that we are better than the compiler in some points. So we want to provide our information to the compiler process. For example, the analysis, we can refine some analysis information. We can ask the user to give us some information that the analysis cannot derive, for example. And with this information, then we can refine the analysis internally or enable some optimization that will not be safe without this additional information. And here there is a range of examples. So there are languages which are implemented as pragmas, and a striking example is OpenMP. But lately we have OpenAC, which follows the same kind of strategy, so pragmas. And StarSS is also another research project from the Barcelona Supercomputing Center, which also relies on heavily on pragmas. The nice thing of pragmas is that if the compiler cannot handle it, the compiler can just skip it, and it will compile the code without taking into account the the information that we provide with Pragmas. And there are also tools like compilers that usually define their own Pragmas. For example, the Index compiler had for a long time this vectorizing compiler, vectorizing Pragma. GCC has its own Pragma for either the debugging information, alias information, and so on. So we have a wide range of Pragmas. And the main problem is that Clang supports very few of them. And if you want to add a new definition of a Pragma, it gets very, very complicated. And here an example is what Clang provides you for adding a new Pragma. So basically you have this class, it's an abstract class, Pragma Handler, which have this virtual method. It's a pure virtual method that you have to redefine in your own derived class to implement a specific Pragma. And you can notice here that the only thing you get as input is the preprocessor instance. And that's it. The work that you have to do to parse the Pragma, it must come from you. And additionally, you have some classes for example, create hierarchical namespaces and so on, which are just some kind of syntactic sugar, so not really interesting. So now we see, we look at an example of what the user has to write in order to support a simple Pragma, like this Pragma unused, which wants a comma-separated list of identifiers. So the unused keyword, it's parsed by the preprocessor, and it's used basically to trigger your Pragma handler. So this is already taken care, and what the user has to do is to make sure that the syntactic definition of the Pragma is correct. So what we do here is quite trivial, but it's a lot of code, as you see. So we just check, we get the next token from the preprocessor, and then we check here whether this is an opening bracket. If not, we just say, okay, this is not conforming with the specification of our Pragma, so we just throw an exception, for example. Otherwise, we expect, so we parse the opening bracket. Now we expect a list of identifiers. So we define this variable just to remind us that the next thing we want to accept is an identifier. Then we consume the next token. We check whether there is an identifier, and if it's true, then we switch this to false, because it means, okay, next thing that comes must not be an identifier, so it might be a comma or the closing bracket. And if here we do not get an identifier, we can just say again, okay, this is wrong. I'm also going here. Okay, this is wrong, and we have to finish. Otherwise, if we expect a comma, we can say, okay, now we got a comma. Let's switch again this lex ID to true, because next thing that comes is an identifier again. We continue this for loop, and when we find the final closing bracket, we can just say, okay, we successfully syntactically match the Pragma. We can just continue with our work. Otherwise, we found something that was not in our specification, and we give up. So it's quite easy, but this is not yet all the story. So next thing, indeed, that we have to do is check the semantics of what we parse. So for example, if these identifiers are actually correct identifiers within the code, or these are just a string that the user is writing there with no meaning. So the way this is done currently is you add a new method in a SEMA class, and usually this is called act on Pragma, the name of the Pragma. And then since in SEMA you have all the information about the context, the scope, the parser itself, you can easily check whether the semantics of your Pragma are correct, and you can store new variables within the SEMA in order for the next statement to apply the semantics if your Pragma is referred to the next statement, or you can store information somewhere else as a notation. So here there is a various way of doing this, so there is no specific pattern. And the main problem here is that basically none of this is automated. I mean, many of the things could be just be automated and without the user doing all the work again, but currently there is no such a thing. So adding a Pragma requires a lot of work. And here, basically the main motivation why this is Clang is not really Pragma handling. So first of all, the user has to access directly to the lexer, which means that you have to know how the lexer works, and This is added work you have to do, and probably you don't care that much how the lexer work, you just want your Pragma to go through the compiler. And the important thing is the second point, that there is no way currently to add new Pragmas without touching the SEMA class. And what you have to do, you have to extend the SEMA class, and if you don't want to release your code in the mainstream, it means that you have to provide patches that the user who wants to use your Pragmas compiles together with the code. So then you have to update these patches every time. So it's a very complex thing. It would be much easier if you could define a new Pragma using the lib tooling interface, for example, where you just provide the new library which implements OpenMP, and this is a separate library. Who wants to use it, link it with the compiler, and that's it. So the solution I propose here, it's not that complicated. I mean, my idea for the design of this framework are these 3 points. So basically, I want to add new Pragmas without touching core classes of Clang, so everything has to be externally done. And the second thing, I don't want to specify to say how my Pragma should be parsed, but I just want to give the declarative form, and then have some kind of engine that does it automatically for me, generates error for me, and also extract the information which I want from the Pragma automatically. And also the mapping of Pragma with the statements or declaration should be done automatically. I don't want to redo this every time I want to have a new Pragma. So Pragma definition. So what I would like to have is just a simple extended Bacchus normal form to basically define my Pragma, and then from this have a matching algorithm that check whether my definition match with the input stream of the lexer. So ideally here we could define this unused Pragma using this symbol notation. But if you think about it, we could write this as a C++ expression or a C expression here, so we don't really need C++ yet. But we can have a token which means that we expect to have a keyword which is called unused in the input stream. And then we could say, okay, this keyword should be followed by an opening bracket, and then it should be followed by an identifier, and then it should be followed by something which looks like a repetition from 0 to an infinite time, an infinite amount of this expression over here, which is a comma followed by an identifier again. And then everything has to be followed by a close parenthesis, and at the end of directive, which means that we parse basically all our directive, and there is no spurious text at the end of after the closing bracket. And actually, this is something which I was inspired from the Boost Spirit parser, which is a very interesting parser generator written in C++ for DSLs. And now we can do another step to make it more eye candy. We can just use some convenience operator, because in C++ we can do that. And we rename this A followed by B, just the right shift operator. We can just say that the repeat is just the star operator. And we can rewrite our specification just as a normal C++ expression. And there you say that this is the same thing as before in a much more compact way. And of course we can go on and add more operators which have a rich semantics. For example, we can have a choice operator where we say that at some specific point in the input stream there might be A or B, and whenever there is A or B, this is a match as a true match, and otherwise it will fail. And we can have an option operator which say that the next token might be A or nothing. So the empty rule, which basically skip this rule and continue with the parsing. And we can use brackets to basically control associativity and priority. And this is basically everything we need to provide definition of for any Pragma you can think of. So now, if we look at the structure where we have these operators and at the leaf nodes, we actually want to refer to tokens which are defined by the Clang lexer. And this is done in a very simple way. We just use this X macro, which reads the token kinds from Clang, and then it wraps it with this toc class, which over there gets the token kind as a template parameter. And this is basically allow us to import all the token types from Clang. And beside this, we have I define 3 token, which I call semantic token, because they're not just a simple token, but they also carry some semantic information. And for example, the keyword, as we've seen, so the keyword is an identifier, but it has to be the same as the string argument which is provided to the keyword constructor. And we can have a var, which is basically a placeholder for an identifier, which is also a valid variable, so a variable which must be declared within the scope of the program. Or we can have an expression, which is basically a sequence of tokens which it's a semantically valid C or C++ expression. And this is quite important because in OpenMP, Pragmas, for example, in some clauses like num threads, what the user can specify there is just a full C expression. So you can just have a very complex expression, and you don't want to rewrite a full parser expression using, for example, this framework, or more uglier if you have to do everything by hand. And I will explain how we do this later. So this is just a trick. So here we have our classes representation, and here I just put this to show that we use this kind of composite pattern which allow us to compose all these operators together and to build complex operations. And an important thing to notice here is that every concrete node of this hierarchy implements this match function, which is basically the main engine we use for parsing. So how parsing is done, this is the most easy thing of the whole framework. So what we do, for example, when we have the concatenation, which is A followed by B, so we basically enable backtracking at the beginning of before starting matching, and then we recursively call the match on our left-hand side and the right-hand side expression. If they both return true, so it means that a match was found, we commit the current state of the preprocessor, and we return true because we were able to match A followed by B. Otherwise, we just backtrack to the beginning and we return false, saying, okay, this we didn't manage to match it. Next rule, please. And the next rule, please, is, for example, whenever we have a choice where we have A or B. And the way we do this is we enable backtracking at this point. So here there might be some too many backtrack points enabled, but this is working, so it's probably not efficient. And what we just do, we check whether the left-hand side has a match. If yes, we commit and then return. Otherwise, we backtrack, enable a new backtrack point, and we check with the right-hand side, and that's it. And the idea here is that with this code, we enforce an ordering on which we evaluate the rules. So the left-hand side is evaluated before the right-hand side, and when you write your rules, you should account for this ordering, because you could have a smaller rule which is matched before a bigger one, so you have to write the longer rules first and the smaller rule later. So at the end, what we have is just a simple top-down recursive descendant parser which uses backtracking, which is not particularly efficient, but usually if you have a small DSL, this is not a big factor in the whole overall computation time. And this is, for example, a way that you can specify the for clause for the OpenMP. And here we have that the OpenMP for is just the keyword for. This is important from the Clang keyword definitions. And then we have a number of clause. And a clause can be, for example, the keyword first private followed by this var list, which is an opening bracket, a list of variables, comma separated, and the closing bracket. The same for this last private. You can have a collapse which get an expression in brackets, or you can just have simple keywords and many other things. So this is quite interesting for our project because, for example, we were not happy with the way OpenMP handles some of the enable to parallelize the code, especially if you want to consider energy aspects. So we extend OpenMP with something called OpenMP Plus, and we just add new rules in this way, and in like half a day we had a new OpenMP Plus implemented with no very little effort. And so how we deal with this expression? So here, this is an egg, and this is probably the reason why this is not in the mainstream Clang, in upstream Clang. So the idea is that we don't want to rewrite the parser for expression because Clang already can do that for us. So why do not expose the parser itself? And basically we do this by declaring one class, this parser proxy, as a friend of the Clang parser. And this enables this class, which is our main entry point facade for using the Clang parser, to just call the parse expression method, and basically which use the Clang parser to parse expression also in Pragma while we are matching Pragmas. And we use the same for parsing, for example, variable declarations and so on. So this is our main entry point to the Clang parser. And this is kind of unsafe because we expose the whole parser to external use. But I think this is the smartest way of having expression parsed in Pragmas without getting crazy. So next important thing is how we extract useful information, because until now we saw that okay, we can parse the syntax, but many of these things we are not interested in. So we are not interested in the position of the commas, for example, the brackets. This is all not interesting. I mean, here what is interesting is that this is an OpenMP for Pragma. There is a private close, and the A and B are private, and then the scheduling is set to be static. And we do this by having an object which we call a match map. This match map is basically a map between from a string to a vector of pointer union class, which is either an expression or a string pointer. So we can represent the information on the previous Pragma simply like that. So we have a 4 mapped to nothing. Then we have a private keyword which is mapped to a list of these are declaref expression pointers. So A and B, which points directly to the declaration of A and B. And then we have that our schedule is the string static. And what the user has to do is to get this map from the framework and do his own operation. So he has to extract the interesting thing and apply the semantics to the nodes. And how we control this, we have 2 additional operators. So one, it's the array index operator, where we specify which is the key that should be used to map a specific expression, so tokens which are parsed in a specific expression. Or we can use the unary not operator, to the binary not operator, to just say that we don't want any of the tokens within the expression A to be mapped in the final map, in the final match map. And an example of how this is done. So for example, here we are not interested in the parentheses, so we can just remove them from the final map. And then whenever we have this expression, we assign a different keyword. So the first time we parse this, when we find the first private, all the variables within this first private will be mapped to the keyword first private. When we apply this rule, all the variables in this rule will be mapped to the last private keyword. And this basically allows us to extract this map, and from this map easily apply the semantics. So the next thing is mapping of statement, so Pragma to the statements or declarations. And here there is the second hack that we have to do in order to perform this mapping. Currently what we do, we have an extended SEMA class, which basically do the mapping whenever we encounter one of these act on compound statement, if statement, for statement, basically the place where we know that might be Pragma operation. whenever we find this, we run an algorithm which checks the source range of the statement. We are reducing at that point, and then we find we have a list of pragmas which have been correctly parsed. So every time we correctly parse a pragma, we add it to a list which is in SEMA. And then whenever we close one of these statements, we basically check the ranges, check which of the pragmas in the list are within those ranges. So the pragmas are ordered by position in this list. And then we try to map the pragma to the statement to which it's associated to. And this is then done by setting a pointer to the actual statement in the pragma object that we generated whenever we find a new pragma. And this algorithm is based on source location. So basically we look at the source location and then we check that immediately after the pragma, the statement which starts immediately after should be matched. So we account the first situation where we have multiple pragmas all associated to the same statement. So this is accounted for. And also we account for situation where we have an OpenMP barrier, which is the only case where it can happen at the end of a compound statement. Because you understand that if you have an OpenMP barrier at the end of a compound statement, you don't have any statement to attach it to, because this is the last statement of a compound statement. So what we do there, we just add a new statement to the compound statement, an empty statement, just a NOP, and then this OpenMP barrier will be associated to that NOP. So it's not very nice to see at the end having this NOP in the no-hop in the generated AST, but it allows us to do this mapping in a very general way. So now finally we go how you use this framework. So basically you define your own class. So for example here we want to define OpenMP pragma critical, extend from this pragma class which is defined by the framework. And you have to define a constructor which gets the source location of your pragma and an instance of this match map, which will be generated by the framework. And then inside your constructor, basically you access the match map, and then you set your private field of your class accordingly of what you want to do. And the way we register this pragma with Clang, it's easily by saying add pragma. We have this utility class which gets the actual type of the pragma we want to generate whenever we concretely match something which looks like this. So here you have your definition, here is the head of your pragma, and here you provide the class which is the implementation of that pragma. And what we do, we just have a simple driver which loads translation units in this case. So this is just instantiated Clang instance, and it redefines the parse AST with some additional thing is not important. But whenever you have a translation unit object, you basically can get the compiler instance, which then allows you to access the AST context, and a list of pragmas which are matched to statement in the AST context. And basically when you have this list, you can access to a particular pragma and then do some check on the location, get the type, check whether the associated statement is a statement or a declaration, and get it. So here you will get a pointer to the statement in the Clang AST. And of course you can cast the pragma to the actual type and then access to the information you are interested in. So we choose this solution because in our compiler we apply the semantics of OpenMP after we rewrite the Clang AST into our own intermediate representation. So there was no need for us to react, apply the semantics of OpenMP directly in SEMA. But you could choose this solution and it will not change much of the framework, just force the action at the moment of when you match the statement to the pragma instead of storing as two separate things. And here there are some performance numbers because everyone loves performance numbers. So what we have, we support a lot of OpenMP codes, and in our framework we implement the entire OpenMP standard. And here I just run a test where I test the front-end time, so that the time for the front-end to build the AST and produce this list of pragmas with the association to the nodes in the AST. And this is the time that took to run the front-end on this BT, which is one of the NAS parallel benchmark. If you are familiar with HPC, these are the only OpenMP codes that we are using in every paper. And you see that the time when we enable the OpenMP support, it just go up by 5 to 10%. And the number of pragmas that were encountered in these codes is reported here. So there are quite a lot of pragmas. These codes are around 2,000, 3,000 lines of codes. And so performance-wise, it's not that expensive. We actually spend some time on making it performance efficient. And so finally, I conclude this talk with two things. So first of all, this code is not private. It's open source since some time now. It's like 6 to 7 months. And you can access it on this GitHub project. If you search for a clump, which should be Clang OpenMP support, you will find it. So this is not just, so the OpenMP is implemented in this project, but you can define new pragmas as you want. There is the OpenMP as an example, so you can start from that and then define your pragmas. And there are examples, test cases, so it should be quite easy to use. The only problem is that we rely on a couple of patches to Clang to actually apply this friend trick, and also the extension to the SEMA class we need for the matching. And this is the only thing that we actually do. So there is a 100 lines patch that you have to apply to Clang, and there is a script which does it automatically, applies the patch, compile Clang, and install it in your system. And then you have to compile this project with this modified version of Clang. And so why this is not yet into Clang? So first of all, time constraints. But this could change in the near future. Since I'm close to finishing my PhD, I could have more time for development instead of research. So I could spend some time on fixing some of the issues in the current state of this project. I mean, it's quite stable. As I said, we compile many OpenMP codes, NAS parallel benchmark bots, which is a Barcelona task benchmarks quite easily. It requires some restructuring, also because I use a lot of C++11, which I don't know what is the current policy of LLVM about having code C++11 in main upstream. And also a lot of template metaprogramming, which I seen is not very welcome in the mailing list. And it depends. I mean, whenever we want to integrate this into Clang, it depends on the level of interest that people have. I mean, I have no problem of doing it. It's a lot of code, so it will require probably a long time for getting through the code reviews, but it could be done. But we still have to solve the problem of opening up some of the internal, like the parser, to external tools like this, so that it could be easy to develop this kind of extensions directly as a tool interface. And this concludes my talk. And here I have again the link to the project. And I welcome any contribution. And if you have questions, I would like to reply. Yes.
Any questions?
So in your parsing examples, there was one thing that I didn't see at all, which was how you report nice friendly error messages.
Yes. This basically, from the definition, at each point where we have a choice point, I generate a list of what will be the correct continuation from that point. And at the point then I finally get the error, I build up a string of possible choices that could be at that position, so I just create a message saying, okay, that position was expected this or this or this, but you wrote this other thing. And yeah, this is something that probably is not completely 100% working. I mean, it works most of the cases, but the way I wrote it, it was like in one day, it was very messy. Probably it requires some reviews, but it worked most of the time, so I just I just use it.
Yeah. So if instead of going with this, if you just kind of went with a more lightweight approach of using the current Clang Pragma system, right, and then just having the parser scope opened up to use, I mean, couldn't you get a lot of the benefit just from that?
Yes. I think the only thing is opening up the parser, because the other thing I do now is because when I developed this at the beginning, I started with LLVM 2.9 or 2.8, and the SEMA class was virtual, and it was a very nice thing because I could develop my extension as a derived class of the Clang SEMA, which runs my algorithm, and then it invokes the act-on compound statement from SEMA, and that's it. But then this was changed, and now I have to re-enable virtual inheritance in SEMA. So my patch basically just re-enable virtual inheritance in SEMA, but if we just bring this code inside SEMA, then it should work. There is a one patch solution which then should allow other pragmas to be automatically handled. But that's the only thing I do. So they privatize the parser and act on SEMA class. And then you should be able to just have extension as a library.
You said at the beginning that researchers love to play with pragmas,
yes.
And I've got a question. Do they love to play with attributes too?
Probably when they will be supported, yes. I don't know. I mean, many of the language extension we work with in HPC are Pragma based. We really never found any attributes extension that I'm aware of. So that's why we focus on Pragmas. But I mean, the two things are so similar that probably if you have an approach for Pragmas, should also take into account attributes as well. I mean, you should have combined approach that it should work for both of them, I think. But yes, attributes are really not aware of the development there. So I would actually like to study them.
Why don't you want to use enter tokens method and to expose all tokens from Pragma directly to parser?
And then again, use what?
There is a method enter tokens which allows to expose all Pragma tokens directly to the parser and use standard parser to parse Pragma to use semantic analysis without any problems. Why don't you use it?
Because I was not aware of this. But then how you still have to do your parsing inside SEMA, so you cannot just have it externally as an extension to the normal way this is handled.
I use this method for parsing OpenMP pragmas and.
Yeah, but you still have to have your implement. But you still have to have your implementation into the SEMA class. You cannot just have it outside SEMA.
No, I can use SEMA because all tokens are directly exposed to parser, and I parse Pragma just like a kind of statement or declaration.
Okay.
So I can use all standard methods, including semantic analysis. So no problems with it at all.
Yeah, I mean this is not a limitation. I mean, I use this technique because this is the thing I just found by looking at other implementation of Pragmas in Clang 2 years ago. They all follow this strategy of just check the syntax in the Pragma handler method and then add in SEMA some action for the specific Pragma. But if this thing now it's possible, I can just rewrite this in a better way. Yeah, I will have a look with this?
Yes.
Thanks.
Any further questions?
Okay, how do you construct a Pragma parser proxy?
This is just a class which I...
Because you need the Pragma object there. The parser object.
Yes, so basically when I redefine the parseAsked method, I don't use the standard parseAsked method from Clang. I have my own version where I build the same object, and then I build this Pragma handler, where I pass the parser inside the same as an argument. And then basically I create the parser into parseAsked, and then I pass the parser instance to my proxy object.
Okay, so
and
you
then from
use
that point,
a patch there at this point.
yeah, no, I just read it because the parseAsked is just 10 line of code. I just have my own version of parseAsked, which basically is the copy of the normal parseAsked, which at the beginning do these 2 steps to basically pass the parser to the proxy object.
Okay, thank you.
No.
Final question? All right, in that case, let's thank the speaker again. Right, that was the last talk here because the next talk is